Okay, hi again. So this is our CAE window now. So this is I would say this is an assembly that we have already shown. So first, again, I will go with the parts. So if this is the forming 2D die I have shown. So I have modeled and we have shown the mesh. It's quite big, I would say, but at the corners I have tried to make it a big. I would say fine, and you can see the if I'm seeing the assigned elements, you can see it's a normal coupled temperature because I have modeled this as a, we know it's as a it's a deformable body, it's not a rigid anymore, so I've used the coupled temperature and linear, so it's not a
Yeah, so maybe it might be interesting to see there are a lot of options grayed out.
Yeah.
Because compared to a purely mechanical element, there are some limitations that Abaqus gives you in terms of, I cannot play around with, let's say, the distortion, the hourglass control and stuff. So a lot of the things are restricted and can only be used in the default option. So that usually shouldn't concern you that much, especially if you use standard and geometric order that is linear. But it's just interesting to know that you cannot play around with these type of elements as you might be used to, especially in for axisymmetric problems.
Exactly.
So this is you see again here. This is axisymmetric, and that's quite important to maybe point out that we are only dealing with axisymmetric problem here right now.
Yeah. And so the same way the lower die, but the sheet, as we have already told, it's a radius of 100 mm and thickness 1. And so if I go with the materials now, I have given I have given the hot steel 22 Mn5. So I have told the conductivity and specific heat are necessary when we are doing a thermal mechanical coupled. I've also given the mass density, because if you're giving a specific heat, or we need to know the mass density, and I've given the elasticity like Young's modulus and the Poisson's ratio. And now with the plastic flow curves, I have given for the all temperatures, we can see from 25 500, and it's and I went till like 700 degrees centigrade, because my sheet now would be at the start would be at this temperature 600, and I've given up to 700 degrees centigrade. So this is the plastic data that I've provided. And
what about the heat generation?
Yeah, in this specific case 2D, I haven't used this heat generation.
Can you maybe explain
why?
Like,
okay, why I wanted to make it a bit simple first, and so later I haven't used it in 3D and everything. So
but okay, so that might be one explanation, I would say.
Okay, why haven't I used technical wise, you mean?
Yeah, exactly. So I guess the correct explanation, and it's actually okay to not use it here, even though we have emphasized it's important in forming operations. Just think about it. So you generate in general, so you can say that the volume times the strains is roughly what you give an idea or a feeling for how much heat is generated. And your volume in this sheet is very small, again, compared to its conducting surface. So there will be a lot of heat loss from the sheet to the die because of the large contacting surface area and the steep or the high difference between the temperature of the sheet and the die, which is like initially 575 degrees. So whatever tiny fraction of heat that's being generated, it's immediately conducted to the die. So in this case, but you guys can definitely check it out, that you won't see a big difference if you activate the heat generation, especially given the fairly slow process speed. Yeah. So it's fairly slow. At 2 seconds, it gives the heat a lot of time to dissolve into the dies. So whatever heat is generated, you would barely notice because the dies will all take it in and extract it from your sheet. But let's say if you go to a process speed of 0.2 seconds and you have a thicker sheet, so there is, like, in absolute terms, more heat being generated for the same contacting surface, so you reduce this ratio surface to volume, then it might be really interesting to activate it and see the difference. So I definitely recommend to play around with these with this specific heat generation factor and activate it and deactivate it and see the effect on the temperature evolution.
So if you wanted to do it, you can find it in thermal inelastic heat fraction. So this is how it's 0.9, this is 0.9, I can keep it. So that's the one thing. And after the property, we have already talked about assembly, and now we'll go about the step. So when I'm defining the step, I've just done with one step. So this step includes both the forming and the retraction. So for this type, I need to use the amplitude for this, which I would be telling about later. But this is how the window looks like for a couple temperature displacement. And here, one important thing where we can both do either transient analysis or the steady state analysis also. So and the time period energy on, it should be
this course could be called just do the freaking energy on. But maybe you can elaborate a little bit on the steady state versus transient, for instance, for a start.
Okay, I mean my analysis, like, it changes with respect to time, the temperature, so it's a transient. But there might be some cases where we are looking for a very quiet quasi-static or time taking processes where it can be steady static. I mean the time increment, it would be always constant. So for the change in the temperature, so that states can be used for the steady state. But
so usually in forming we have transient
exactly.
problems. So sometimes we have technically fully Eulerian problems, like the extrusion, like I say, excluding the beginning and the end of an extrusion process. But then we would switch the mechanical part to steady state response. So this is something we usually only consider in very certain specific places. But what about this automatic stabilization?
This is one thing that we would explain later in the contact controls. So this it's like a trick to make convergent easier, or especially this is useful when my retraction phase where the contact is separating. So that's a situation where I have tried a lot, which this is the one which is normally
this is default.
This is the default one, I have used this one because this is one thing which I've seen in Abaqus some videos or Abaqus manuals, and I've seen it's one trick which we can try if there is a problems in our convergence, especially due to contact. So which we would see it later in our results phase, like what is the problem I got and why I have changed this. And but the incrementation, so maximum increment, number of increments, it's my wish. So and the initial I have taken as 0.001 and the maximum, and this one thing we need to specify also, telling that how much allowable temperature change per increment, and this can be as maximum as possible.
Because this can also affect your convergence
issues a lot. And the other one which we can see, this is the one I have told in the default one where we have the user solve a default for a displacement analysis, and we can choose either unsymmetric or symmetric. But in these conditions we only have unsymmetric. It's the only way it can. And so the other ones are fairly the default one, which haven't changed anything. So this is about the steps, and now I would go with the interactions. So as usual, interactions, the first one, I have made the surface to surface contact, and we know it's always a finite sliding I can use. So as a surface to surface, and here the red one, the die surface is the master surface, and the sheet is the slave surface. And I didn't go for any adjustment, so it's like the normal one. But if you can see the interaction property, this is the interaction property I have used. So the tangential behavior, it's frictionless, which we can play later on, like if you want to change. And I've used the normal hard contact, but this can also might be an important thing which I would like to focus when we can experience maybe in some critical 3D simulations, which I have experienced some of the convergence problems there. It's better not to give this hard contact. So which you have already specified in your previous videos. And this is the one which we have talked about, the pressure dependency, and I've given the last point as it is. I haven't done any extrapolation, so the Abaqus would take care of it. And
so you use the data you found in a paper right away. So this is, if you don't have any data at hand that you let's say, personally generated. So it's usually always a good fallback option to just check the literature and see what is out there, what is known. And it might not apply 100% to your case, but it at least gives you a start. And I guess you used millimeter and megapascals here. So this must be in line with your flow curve definition, right? So that's very important to always check that you use a consistent unit framework for this as well.
So as we have shown in the previous slides, there is a very good literature if you want to think about hot stamping. There is a master thesis done on hot stamping. So I have taken quite a lot of data from that source, which we have already specified in the simulation.
So here again, it's interesting to see that you, as in many cases, if you deal with the thermomechanically coupled problems, that you can activate the use temperature dependent data. So you can think about it as so we talked about this contacting or the two contacting surfaces which are flattened out with increasing pressure, and therefore the effective true contacting area increases over time. But usually with a higher temperature, this effect increases as well, because the body itself gets softer. So you know that if you just think about it as a microscopically, so these hills and valleys, right, they are flattened out more easily if the material is softer. So given the same pressure at higher temperature, so you will usually see a higher conductance. So to further improve on this regard, maybe we can switch back one more time to this slide here. So this curve could actually be temperature dependent. So if we say this is for the both bodies being at let's say 25 degrees, and you usually define it for both bodies being at the same temperature. So but it would look a bit different if it's at 200, 400, 600, 1000 degrees. So if you want to further improve the accuracy, you could include temperature dependent data, but you have to consider, so where does this data come from? Can you generate this data on your own? So usually there is always is it a good investment? What's your ROI, right? Your return on investment. So it would take a lot of time to generate, like, experimentally, this conductance over pressure as a temperature dependent function. And the influence, what you guys could do is just define, let's say, room temperature and 1000 degrees, and just give, like, say, the 10-fold values, and just see the effect of this if you activate it versus not activating it, right? So there you assume a constant conductance pressure relations throughout all the possible temperatures. So all the things, just play around with it, see the effect of it, and understand if it's really so important to invest the time to make the simulation more accurate at this point, right? There are so many simplifications in such a simulation, and do you really want to invest the time to get this one even more physically sound? So always keep that in mind, that just think about your return on investment. That's what I can.
Exactly. And the other one, the heat generation, this is what actually is not required, but I've wanted to show here, like, it's depending upon your friction. So if I have already given my friction, then this could be useful, like how much heat I can generate from my friction. I can specify it, and also I can tell it, like, how much is it distributed to the slave surface and everything. So, but this case, it's not important for me. So
because you use frictionless.
So,
but it's interesting to see that the default option is 1. So technically, the entire dissipative process is being resolved as heat energy. So, and usually, there is an assumption that you do a 50-50 split of this particular energy. But in some cases, you can say, if you, for instance, know that your slave surface is usually much hotter than your master surface, then you could argue that the master surface will take in a lot more heat than like right from the beginning. So, but usually a 50-50 split it's okay.
Might be this value might also depend on the thermal properties of the materials.
Exactly,
So,
exactly. So
but this is not required for mine. So, but I just wanted
but
to
I
show
guess we talked about activating friction later on. So
exactly. So this would be a really good thing we need to activate actually.
Yeah.
So makes sense. And the contact control. Yeah, this thing actually quite different. Why I have introduced this one? It would be actually no stabilization. This would how the window looks like. But I have made an automatic stabilization, and I have also changed the tangent fraction. And I think it's better if we explain this why I have introduced it and to show the results and then tell it like.
Yeah, but I guess I talked a little bit about this in my last video on deep drawing. So, and technically we are back to an implicit deep drawing step. So for the guys who haven't watched the videos, I will make a link to my previous video here, because there I guess talk about all the aspects in even more detail regarding the stabilization. Yeah.
So that's the thing here. And so now going with the loads or. So yeah,
you shouldn't. What about the constraints? I see 2 constraints there.
This is one thing I would explain with the steps. So yeah, there is an initial step. So in the initial step, I have given 2 boundary conditions, giving that the boundary, the lower die is always fixed. So it's an encaster. So I've given it in the initial boundary conditions itself, and I've also created the symmetry. So it's like this type of symmetry, the X1. So actually it's an axisymmetric, so I don't need to give it, so it's an like over constraint, but so
I was just about to say to be sure.
Yeah, just to be sure.
No, but what about the constraints here?
This is the rigid. I would come into this. This is the rigid constraint. So but I will go with the first the initial temperature. So this is where we define in our predefined fields, and I think you can see it here. So the initial temperature, this is where we will tell like can we get from the other data, but this is not possible for a thermally coupled mechanical simulations, especially in Abaqus standard. So and I've given as I was told, the dice would be starting, it would be at 25 degrees centigrade. So at the room temperature, but when we are doing the process in a mass scale, I think the temperature might increase for every operation. So that's again one thing we can think of, but now I'm thinking that I'm just doing the process just for once. So I've taken 25 degrees and the same temperature I've given for the lower die, but for the init sheet we have told, we didn't think about the heating of the sheet from the start from 25 degrees through an oven or something. So we have just given the initial temperature.
But
600.
Just to get me up to speed again, didn't you mention that you can't use these predefined fields in a Abaqus standard simulation? And this is going to be a Abaqus standard simulation.
Yeah,
right?
I mean, this is a predefined, maybe I would open this predefined here. If it's a predefined field in the initial, I cannot use it, but in this one I'm telling about, if I'm using in the later steps to use the results from the other simulations, we cannot use it. So only in the initial step we can define this. It's like like a boundary condition. So it's like,
oh, you mean you cannot introduce, let's say, a second a second body later in your simulation and use a predefined field?
Exactly.
I mean, you could technically give this predefined field in the initial step as well for this, let's call it a second body, but you can activate the body later on. So
that's
okay, now I see what you're getting at. So you can technically still use it, but you can only use it in the initial
that's the
step, like
exactly
initial. Okay, because from there everything else is being computed during the simulation. Okay, got it.
And so we have seen the lower die, the boundary as I've told all the boundary conditions, and the forming load I've kept as I have given the displacement boundary condition according to the time requirement of my process. So and here we can see I have given a forming amplitude. So I'll go to the amplitude. Why I have given is I've created only one step. I don't want to create 2 steps, because when I'm creating 2 steps, I realized I'm having a lot of convergence problems. So that's the reason why I have defined the smooth step, so that for up to 2 my forming step is completed, and I've given a certain time for the die to stay on the sheet, so that the temperature would be taken away according to this. Also I would explain why I have did like this.
So you stay on like in a
contact for like
0.1 seconds.
Why I have given this because as we know, the main idea for doing this hot stamping is my microstructure should somehow be martensite or martensitic at the end. So that's the reason why my cooling curve, there will be a critical cooling curve, which we'll say later in the results file. But for getting that type of curve, so getting my temperature below that cooling curve, so that's the reason why I have given this an additional, I would say, a stay of the die on the sheet, and then later within 1 second it goes back to its position. So I have given the smooth curve, and I have given this to the displacement thing. So this is all about, this is all about the...
So if you set up a job according to what Manish just told about, it should run perfectly fine. Do you have an ODB that we can take a look at, just how the final simulation looks like?
This one, I would select it there like quite a lot. This one is the final ODB. So
maybe you can check just all right, let's take a look at the results of one of your simulations here. And if we look at the final step, we see, okay, so the general approach was you have the forming operations, then you just stay in contact, and then you retract the upper die. Whoosh. So if we take a look at this in terms of an animation, we see there is the forming step, then there is, let's say, the heat transfer step, and then there is the pretty fast retraction step. So don't get confused. We took an output at every increment, and maybe we can also go back and show the field output once more, because here
every increment.
So first we took every increment to see. Then it's easier to visualize where the simulation takes a lot of time. And also I wanted to point out that under thermal you can activate the things you're interested in, right? So nodal temperature is usually the one we're looking at, and the fluxes. So there's a lot of things you can take a look at and analyze regarding the thermal simulation. So if we switch back to our simulation, and we could select the nodal temperature here, and for instance we would see that the initial sheet is at 600 degrees, and you see already that it cools down just by sitting there, right? And you see that in the area where it's in contact with the die, or almost in contact with the die, it loses more heat to the die, and this is where also the die heats up as compared to where it only sees the ambient. But you can see here on the maximum value, it lost in a second, it lost like 16 degrees C just by sitting there, which is what we expect the sheet to do. So this is pretty neatly, and you can see that the how the heat is also transferred into the body. And if we look at the step time, up to 2 seconds is where the forming step is being ended, and then we have from 2 to 2.1 where we only have the transfer of the heat, and we see that the simulation has a lot of problem to initiate the retraction phase, and this is where we need the stabilization, because this is, for a lot of different reasons, quite challenging for the solver to initiate the reaction phase. I actually still don't understand all the details, but this is just something that we experience, that the retraction phase causes a lot of problems here. And same holds true for the forming steps, where you see a lot of deformation taking place. So it needs a lot more increment in this area here than compared to the beginning of the forming process, right? So it makes sense. So it's always interesting if you take pictures at every increment, that you get a better feeling where it is challenging. I mean, you can also see this in the monitor, right? But it's just interesting to take a look at this. And you see the evolution of the sheet as well, and you see the evolution of the temperature of the die itself. So you have some good ideas how inhomogeneously the temperature changes due to certain circumstances. Right here you have air pockets, you have different strains, you have different contact pressures, right? So this is always not so nice to visualize, but we talked about this. So we have contact pressure dependent conductance. So it makes sense that in these areas where you have a higher contact pressure, there you have a higher conductance, and so this all makes sense, right? Exactly. If you just look at the distribution in general. So I guess these are pretty nice general results. We'll switch back to the presentation once more to talk about some specific details that we've prepared or that Manish has prepared and that we want to talk about and explain a little bit some more details of what you can get out of such a simulation and things you have to consider when doing so. So see you in PowerPoint.